Okay, we're asked to give it an example where a complex number raised to a complex number equals a real number. And they're saying you should restrict yourself to complex numbers where the b is not equal to 0, all right? So it's got an imaginary part. Okay, so just to review what we've done in the past, certainly what you've done in Math 100, you've written things like this down, where z equals a plus bi. Now b is not equal to 0, by the way. Now in this course, we're letting what's known as the modulus be equal to this over here. Let me kind of remind you where that's coming from. And we have a real part. Let me get my black pen out. We have a real part and an imaginary part over here. And then, some value over here. And let me just put down AB with the understanding this is some angle theta over here, all right? And, we've written this down before. The length is r over here, and the r would just be equal to, some real number, a squared plus b squared, and that equals r. And, since b is not 0, this has to be greater than 0, by the way, right? And again, with the understanding that r, again, is a real number, all right? So let me outline that. It's written over here. I got this part over here. And then we write down, these Cartesian coordinates, AB, in terms of sines and cosines. So what do I got? I would have A equals, let's see, that would be r cosine theta, and the b would be r sine theta. All stuff we discussed in the past, by the way. Let me outline that for you right here, right here. And then we put down, what's z going to be equal to? It's going to be the a. Well, the a is r cosine theta. And what's the b? The b is r sine theta times I, all right? And then, of course, we had something new from the prior problem set, all right? And what do we have new? This Euler form, right? So let's put this down over here. And we got something pretty interesting, actually. We have this to write down instead. A little bit more compact, by the way. So we could write this down instead, all right? So r e to the I theta, all right? So just to remind you, e to the I theta is actually cosine theta plus, let's see, sine theta I, all right? Okay, that's what e to the I theta is. So what do we do there? I take the log of both sides. And if you do that, let's write over here. So it's going to be the log of z equals the log, these are natural logs, by the way, r times e to the I theta. And now, natural log of z, not so bad. What's I going to do? Natural log of r plus the natural log of e to the I theta. Relatively simple. Natural log of z is the natural log of r. And this would just be simplified, right? What do you get? You just get I theta. All right? That's sure where we are. We're right over here. All right? So I can get my eraser out. And, certainly old stuff, new stuff. All right? So we have some new things from doing the problems. Stuff that you might forget, but we can always look back at a prior problem to remind ourselves of that. Right? Then what I do is I take the number I, and I write it down in that a plus bi form, which would be 0 plus 1 times I. All right? And then with the understanding that r in this case over here, again, if you need to, look at the complex plane again. And this is the real part. This is the imaginary part. And what would you get over there? That's where I would be. What's the angle going to be? Well, the theta is going to be pi over 2. But it's kind of misleading because what happens is it keeps repeating itself every 2 pi k, with the understanding that k could be any integer at all. All right, what's the r there? The r is 1. And what's the theta over there? The theta is pi over 2 plus 2 pi k. Right, again, with the understanding that k is equal to any integer. All right, so let's go back and let's do this business over here now. All right, put that over here. So you can get the natural log of I, we're dealing with I, by the way, equals the natural log, well, what's the r? The r is 1, plus, well, be careful here, it's going to be I theta, right? So it's going to be I And what's the theta? It's pi over 2 plus 2 pi k. Right, so natural log of I. Well, the natural log of 1 is 0, so I'm left off with just I times pi over 2 plus 2 pi k. All right, let me show you where this is written down. And this is going to be written down the natural log of I. We just went through this business over here, and I simplified it to this over here. All right, then what I'm going to do is I'm going to rewrite that, and I'm going to rewrite that as an exponential now. So I'm going to write it as I equals e to a power. What's the power? I pi over 2 plus 2 pi k. So what I want to do is I want to get, the right-hand side to be just a real number. And, one way you could do that, you could actually raise both sides to the I power now. So I to the I would equal, well, I'm raising both sides to the I power. And what's I times I is I squared. I'll write that down for you. So it's I squared pi over 2 plus 2 pi k. Well, what do you get there? It's just going to be minus 1 now. So it's going to be e to the minus pi over 2 plus 2 pi k. So I found one. What I find that I to the I is just a real number. How many real numbers? An infinite number of real numbers. All right? Now, if you go to Wolfram Alpha and type in I to the I, it's going to give you certainly the easiest one where k is 0, but it will discuss there's others. All right? Now, where's this written for you? Right over here. All right? Do I consider this to be a difficult question? I do. All right? I do want to point out, though, if you're a student in my classroom and you have questions about the stuff that I'm covering and you're doing the optional, good for you if you're doing the optionals. Oh, by the way, I need to insert over here, this is optional. And again, like with any optional thing, the more you take options, the better it is for you. But anyway, for students that are not in my class and want to reach out to me, this is my email address. Thank you so much.